All right, hi, I'm Justin Wozniak. I'm a computer scientist in the Data Science and Learning Division of Argonne National Laboratory, and I'm going to be talking about Diaspora, which is a very new project that I'm involved with, led by Ian Foster and co-PIs and other institutions. And I'm going to talk about predicting and responding to and monitoring faults, especially soft faults. So obviously monitoring real-time processing is requiring more and more complex workflows and more distributed approaches, right? We've all moved away from the centralized approach. We're moving to distributed instruments, distributed compute facilities, and so on. And this is leading to a lot more system complexity. And it's not complexity that we are injecting because we think it's interesting or fun. It's because there's these challenges that are here, right? We have increases in experimental data volume and velocity, the emergence of science-informed AI agents to help us with decision-making, and then the advanced hardware that's driving a lot of this, right? So resilience beyond failures is a big challenge. What I mean by that is not just, obviously something isn't working or something's off. I mean, cases where things are slowing down or limping could be much worse in terms of the cost to your experiment, to your time, right? That something, might have a performance bug that's hurting you or a congestion that's hurting you that you don't know about. And since something has really stopped working, you have a much more serious problem or maybe a problem that lasts longer. So we're trying to build this overarching architecture that helps us provide resilient services. And then we're going to do monitoring and prediction inside of that to figure out whether or not there are any problems. So at the top, we have our resilient solutions. This includes streaming data analysis, flows, Globus flows, your workflows and things like that, data views, long-term campaigns, distributed functions, so functions as a service using Globus compute. And then, of course, the modeling solution that will be helping us find these faults I'm talking about. Underneath that, we have this distributed event fabric. So we're essentially using Kafka, but the team is building on that to make it work better with our services. And then below that, on individual sites, we'll have, of course, the cloud services that are supporting this, MAFCA, and then the instruments and the edge computers. By MAFCA, this is a new technology that's being built for this project, and it's a combination of Mochi and Kafka. So it is a combination of Kafka-like services on top of a HPC infrastructure, which is Mochi, which is this ad hoc data service that you can deploy on large-scale systems. It's been used for other things like key value stores and indexes and things like that in the past, and now we're trying to use it to build a Kafka service. And then, of course, the applications are these long-term campaigns, including situations that are time-sensitive, like I talked about, where congestion and things like that are going to be a bigger problem. So to dig into the architecture a little bit, so we have, we want to be able to provide resilient resources that handle the availability and elasticity that's needed. We want to be able to support live migration from site to site. So in this diagram, I'm showing that we may have some resilient stream that's being presented to the user. It might be time sensitive. So there's QoS requirements. And so this is going to be pushed through this event fabric. And then the system can decide, for example, where to push the underlying work, whether to the ALCF at Argonne or to the OLCF at Oak Ridge. So the QoS aware streams are going to be supported by buffering, interpolation, compression, and all these underlying things that we can do to help keep things running along at a steady rate. And then we need to do monitoring and be able to feedback that to some policy engine that's going to be able to make the decisions to make that actually happen. We also want to provide resilient data views. So that's something that comes out of the Kafka-like experience where you have views on multiple data streams. And then we want to do detection and prediction on that so we can figure out when failures are happening. Like I said, soft failures, slowdowns, congestion, and other kinds of QoS violations. So in terms of resilient resources, so this is being built underneath Globus Compute. We want to be able to have obviously distributed access to HPC machines as well as the edge infrastructure and resources that we want to be able to use. So in terms of the resilience questions, we're looking at how to tell when resources are going up or down, hopefully in advance, how to figure out how to replace them with elasticity or migration or getting new reservations and things like that. Monitoring all of this in the system using that resilient event service that we're building on, which is the Kafka and MAFCA combination. And then again, the load balancing, including support with checkpoint restart and live state transfer, because that's part of the team's expertise. The resilience data streams are the idea that you have transparent resilience. So once you're subscribed to a stream, you're going to be able to get the next record, and our system is going to take care of making that transparent and resilient. So the question is how to translate QoS policies into actions that can be automatically handled, right? So that we can automatically migrate or buffer or do whatever's needed to get things done on time. How to leverage aggregation, reordering, other kinds of overlapping strategies that could be used to fix this. Trading off for alternative computation. So again, this has to feed back up to the science level, right? We need to be able to figure out what else we can do to get things done on time, even if that means maybe using something that's using a lossier compression or whatever else might need to be done. And then how to protect computations and migrate them, again, using the checkpoint restart. The resilient data view idea is the idea that you have multiple data streams that are coming in. You want to be able to cache them and then reorganize and reindex to match whatever the application needs in terms of the data view that it's trying to get. So this is a little bit different from a checkpoint. It doesn't need to be as resilient. It can be reconstructed based on the topics and things like that are in the streams. And then supporting all of this, we want to be able to build predictive models that are going to be able to separate the underlying monitoring and the prediction from the policy decisions that are going to be made. So the idea is that we want to be able to provide a pluggable architecture where teams or maybe even users can drop in models that are appropriate for the systems they're trying to monitor, and then get the monitoring and prediction that they need so that the policy engine can then make these kinds of decisions I'm talking about. So our approach going forward is to collect data sets from teams like the ones here, possibly synthetic ones as well, and then be able to find predictors that can do time series forecasting to make those kinds of decisions. Plug them into bigger systems like VIT, or the virtual infrastructure twin. I'll talk about that in a second. But that's the idea that you're going to be able to cascade these systems and integrate them into bigger systems, network connected systems, and then do kinds of simulations on that to figure out what's going to happen if congestions or other kinds of slowdowns happen. And then we need to deliver those predictions to the policy engines or back to human users so that decisions and actions can actually be taken. We're also going to be tapping into the system I've previously presented. This is the BRAID technology for provenance and tracking. So this will help us track the policy decisions that are made. So if a prediction is made about something and then the policy engine makes a decision, this will help us figure out why it did that decision, because this is going to know about the models and how they've been constructed and what kind of data they've seen, whether it's experiment data, simulation data, or data from other models, which is really the case here, where models are making predictions and influence each other, and then that's feeding into policy. And then at the end of the day, you need to find out, why did my data get collected at a lossier level? This kind of system will give you the provenance that tells you why that happened. So I'll talk about the application driver. So this is a really broad project. It's not just beamline science. The first application is this Slack application where there's collecting data at the edge, retraining at the edge, and then so that involves HPC as well. And then feeding that back to be deployed, I think, on an FPGA while the experiment is running. I think that's the high-level goal. So obviously, there's a lot of resilience challenges here because a lot of components, including this AI training involved, and then distributed data movement, retraining, and then moving that back. So there's a lot of things going on there that could fail. Tychography is another key app for this project. It's been talked about a lot here. So this is Tech and Beister's application at the APS. Another application, though, that's quite a bit different is multi-messenger astrophysics. So this is one of the sub-teams on the project. So this is the idea that we have multiple sensors for astrophysical data that could be satellites, telescopes, other things. The teams here are not always willing to share the raw data with each other, and definitely not with the general public. So distributed federated learning is used to build models in this distributed fashion where they're not actually sharing raw data. They're just sharing the training updates as the model is being trained on this distributed system. So this is another case where you have widely distributed instruments, widely distributed computation, and then you need to be able to move that data around in a resilient way. This is another application from Oak Ridge. This is this idea of instruments in restricted environments where we have instruments that are on private-only networks for policy and system reasons. For example, some of these systems are running on older versions of Windows or have other serious vulnerabilities, possibly just policies vulnerabilities as well. And so they want to be able to actually get these kinds of systems into our distributed network as well. So they're building relays where the data is hopped through some well secured system. And then they want to be able to model all of this as well and model the other applications we talked about. So this is the virtual infrastructure twins concept. So this is not twinning the science, this is twinning the network and the infrastructure, right, that all of this is running on. So this allows us to deploy, for example, these distributed event systems, test them, and do the design and development and what if scenarios. I'll dig a little bit into the predictive monitoring that we're just starting to do. So the idea, again, is to make it easier for users, again, end users possibly, to train and apply arbitrary models to the systems they know about so that they can drop this into a system and then feed that into the policy engine that's going to drive it. So we want simple declarative notation to specify the streams that are going to be monitored and the models that are going to be applied. Again, this is all going to feed into the distributed event stream I was talking about. So this is a relatively simple API to plug into. And then we want to be able to drop in some relatively simple models such as LSTMs and things like that to make short-term predictions about congestion or other availability issues. And then we want to be able to link these models together using that virtual infrastructure twin idea to make aggregate predictions about what's going to happen on the overall infrastructure. We also have been looking at the Lowry diffraction application from Prince. And so this is a nice case for us to look at on the short term as an early kind of use case where we have 3 file systems where the data is being relayed from one file system to the next. It's not too much data. It's a manageable amount of data and a manageable amount of compute time, although we're not really looking at the compute side right now, but we want to be able to figure out, can we make predictions about what's going to happen on these file systems to predict congestion and things like that. So the data collection rate is kind of a trickle for this case, so that it offers opportunities for the policy engine to buffer it, reroute it, and things like that. Of course, it does add up over time. These are all shared resources, like I said, so the performance and accessibility could be variable, but since it's really impacted by other users, it could be predictable as well. Right now, we have some kind of coarse-grained data from this application about what happened when, but mostly on the computational side. We really need to dig in and get into the file system side, so we're trying to dig in to get tuples like this where we get timestamps, I/O sizes, and I/O rates, and then from there, we should be able to plug it into an LSTM. And so what we've done so far is we've rebuilt grid FTP servers to add additional profiling information, and then we can drop that into Globus Connect Personal to essentially replay Prince's application using a very slightly modified Globus. So there's a lot of collaboration opportunities within the project and outside of the project as well in terms of selecting models to run here and how to do pre-training and things like that to collect the performance information we want. And as well, we want to gather more data from other applications, possibly synthetic cases, but other real applications would be really great. So that's my conclusion. So again, in summary, Diaspora is providing a resilient framework for event streams and composable resilient applications where you have wide area networks and where you need this resilience on the computing and data movement side. And it's all being bound together by a few streaming models, including Kafka and Mafka. Future work is to continue with this application development and look at the performance measurements in real applications. Thanks, all.
Thank you, Justin. Question for Justin.
How does this interact with the Globus solution that we saw with Globus Process, Compute, and that? Is this complementary or is it in competition?
No, this is complementary. So this is all going to work within that same ecosystem. But again, like I said, this is a little bit of a wider ranging project where we have wider ranging applications as well as this idea of the Kafka and the other event streaming services. So that's kind of new to the Globus ecosystem.
So if I correctly understand, one of the solutions would be to fill in data streams if some packets are dropped. Isn't there the risk to introduce some artifacts into the process data that will be then lead to wrong conclusions?
Yes. So obviously, I did have a point there about interpolation. I think that would be kind of an advanced solution to the problem. Like you said, could be problematic if we're naive about it. I think that the more simple ideas are things like buffering, caching, and rerouting so that you're actually getting the same data. The next step after that, I would say, would be some kind of more advanced compression. So we do have connections with the lossy compression team at Argonne. That would be something we could do. And then after that would be something much more risky, like interpolating.
Let's thank Justin again.
Thanks.